Hello, my name is Boian Mitov, the president of Mitov Software, and in this session I will demonstrate implementing artificial intelligence with Delphi. As soon as the first electronic computers appeared, an attempt was made to create artificial intelligence. Those computers turned out to be quite good at playing various computer games as well as performing complex mathematical computations. However, when an attempt was made to put camera on a motorized car and have it navigate through a cluttered room, it became apparent that the computers of that age were simply not up to the task. It was not until the early 80s when the next big attempt was made to create such intelligence. The belief was that we can create something called expert systems by taking the knowledge of an expert in a specific field and programming this knowledge using languages such as Lisp and PlotLab. The expert systems had a great promise, but they failed. There were many reasons for that. The amount of knowledge that needs to be processed of the system is quite large. Most expert systems were designed to incorporate the knowledge of a person at a specific point of time. They were not capable of acquiring new knowledge on their own. The fiasco of the expert systems was so big that it damaged the image of the entire artificial intelligence field. After the expert systems, artificial intelligence became popular in the computer games to plan paths and behavior of the different game characters. In the mid-90s, the classifiers started to appear. This was a new artificial intelligence approach. Here is how a classifier works. A special module called feature extractor extracts features from the data. Those features are being sent to a classifier. The classifier looks at those features and attempts to determine what the data is, resulting in output conditions or classes. The classifiers typically are designed to work in one of two modes: to be trained and to recognize. We extract features from the data. In both cases, we send those features to the classifier, but in case of training, we also provide the conditions or the class that needs to be recognized. In case of recognition, the classifier will simply send out the recognized condition or class. There are many different types of classifiers. Neural networks, including perceptron, naive, normal bias, hidden Markov model, kernel methods, support vector machine, k-nearest neighbor algorithm, mixture model, including Gaussian mixture model, decision tree, linear classifier, self-organizing maps, generative topographic maps, and many others. The classifiers can work with different types of training. They can work with supervised training, non-supervised training, or they can be self-organizing. In case of supervised training, we will provide the features and the class to which those features belong, and we'll keep doing that until we train the classifier. Once trained, we start using it with the existing training. In case of non-supervised training, the classifier can be trained after recognition with the same features, but a corrected class in case the recognition was not successful. Typical case of such classifier is a spam filter, where you have additional button indicating whether the email that was recognized not as a spam is actually spam or vice versa. The self-organizing classifiers are designed in such a way that they discover their own classes within the data. They are typically used for data clustering, most often in search engines like Google. Classifiers can be used in many different types of applications. They include spam filtering, computer vision, OCR, speech recognition, diagnostic utilities, industrial control, investment, code formatting, gesture recognition, robotics, games, functional approximation. Now it's time to switch to Delphi and start with our first project. We'll use a neural network to perform function approximation. The idea is that if we have some unknown function which depends on number of input parameters, in this case I will use only one parameter, let's call it x, and for few of the x values we have known y value. So we don't know what the function is, but we know the x and y value pairs, and we would like to perform some form of approximation of the original function. For this, we will use IL neural network from IntelligenceLab. The neural network can be trained in different ways. We will use a backpropagation training method. So we'll drop the neural network component, the training component. For the training component, we'll specify the neural network component to be trained, and we'll specify the termination criteria when the training should be considered complete. For the neural network, we'll specify one input and one output for the x and y values, x input of the neural network and y output, and we'll add two hidden layers, each of them with 6 neurons. In the button 1 click handler, we'll create two matrix buffers, each one consisting of 26 by 1 samples for the x and y values. So we all together will have 26 x-y pairs. We'll clear the scope. We will use a loop to populate our x and y values with some function simulating a set of unknown values. On the scope component, I have added two channels, channel 0 and channel 1. We will plot the training data on channel 0. After that, we'll train the neural network through the neural network backpropagation training component, passing the training data and expected responses. The neural network is trained. Next, we'll test the trained neural network. We'll declare a buffer with only one sample in it. We'll pass 4 times more x samples than we used in the training to see how well the function approximation is working. We'll assign the x values to the test data buffer, and we'll call predict on the neural network classifier. In the neural networks on result event handler, we'll simply plot the result of the classification. Let's test the project. The application is running. Now let's click on the button and see the result. Since the neural network starts with randomized neuron values, sometimes we will not be able to get a very good function approximation. If we get a bad function approximation, as in this case, we can simply run again, and most likely on the next run we'll get much better results. Here is the result of the approximation. With the red circles, you can see the training points, and with the green circles, you can see the interpolated intermediate values as a result of the function approximation. Function approximation was a very simple example of training and using artificial intelligence classifier. Using artificial intelligence classifiers to do face recognition is a much more interesting task. For this, we will use a different classifier called radio-based function network classifier. We will train this classifier to recognize faces. For this, we will use the AT&T training set of faces. The library consists of 10 images per person of 40 different persons. We will use the first 9 images of each person to train the classifier, and then we will test it with the 10th image. We will reduce the max influence field to force it to learn more training. When we click the train button, we'll create a bitmap. we'll create a buffer for the features of 32 by 32 samples, since our images are 32 by 32 pixels. Then we'll iterate through the 40 persons and through their 9 images for the training. We'll load the bitmap from the corresponding bitmap file and add the image to image list. Then we'll display that image into the listbox item. Next, we'll obtain pointer to the pixels of the image and pointer to the training buffer. We'll iterate through each pixel. We'll normalize the value of the pixel and assign it to the buffer. Once, when we have prepared the buffer, we'll train the classifier, passing the features and the expected class, which is the index of the person we're training for. When we click on the Recognize button, we'll set some member variables to count the errors. Again, create a bitmap, create features buffer, start iterating through the recognition images. Again, add the bitmap to image list so we can use it in a list view. Get pointer to the image, get pointer to the features buffer, populate the features buffer with the values from the grayscale pixels, and call predict on the classifier. At this point, when the classifier performs the recognition, onResult event will be called. Inside the onResult event, we'll keep count of the recognitions, check whether or not we have succeeded with our recognition. If the recognition has failed, we'll increment the number of errors and set the result category as 0 and distance 0. Otherwise, we'll get the results category, the distance, which is how different the image appears from the closest training, and we'll check whether or not we have recognized the right image ID. If not, we'll increase the errors. Going back to our recognize code, we'll check whether or not the recognition was successful, and we'll update the information on the list view item. Finally, we'll free the bitmap and we'll print the number of errors. Let's run the project and see the result. First, we'll train, then recognize. You can see that over 40 faces, we have 5 errors, which is about 87.5% correct recognition, which is not bad at all, considering that we have trained with only 9 images per face. And here you can see the correct and error recognitions, as well as the distance from the correct recognitions. We just demonstrated recognizing fixed size 32 by 32 pixel images of faces. In reality, however, when recognizing images, they're usually part of some bigger image, and we are trying to find where there are faces of certain people within that image. Often those faces or other items we try to recognize are rotated, which makes the recognition even more challenging. Mitov Software has developed VisionLab. VisionLab includes scanning component that can be used to scan image with certain X, Y, and rotation step. The scanned images then can be sent to the IntelligenceLab classifiers for classification. Let's take a look how the two libraries can work together. Here is image that contains faces with different locations and rotation. We'll try to recognize those faces. The IntelligenceLab classifiers are capable of saving the training in file for later use. As with the previous project, we'll use radio-based function classifier and we'll train it to recognize the faces. The simplest approach to recognize the faces in the big image is to train with normally oriented images and then use the scanner with X, Y step and rotation. We'll start with a new project, add a radio-based function network component, set the max influence field to 300, and in the form create, we'll create bitmap, buffer for the features. We'll perform the training exactly as in the previous project, and at the end, we'll save the training to a file. Let's run the project. And you can see that we just created a new training file. Now that we have our training, we can use it in a new application. We have again a radio-based function network component. We'll double-click on it and load the training we created. We need a component to load the image with the data to be recognized. For this, we'll use the VO image gen from VisionLab. If we double-click on it, we can open the picture editor and we can load a file with faces to be recognized. We'll set the image gen to be clocked manually by setting the clock source to CS external. We'll connect it to generic filter and the generic filter to image generator. We'll draw rectangles over the recognized faces to show the recognition. For this, we'll declare a record containing position and orientation information. We will also create an array of such records so we can render the results. We'll need to add Mitov containers list unit for the iArrayList container. In form create, we'll create the list and we will manually force the image generator to generate one frame, which will be used for the recognition. The frame will be sent to the generic filter. Inside this generic filter, we'll send the data to another generic filter. This generic filter will send the frame to a sampler. The sampler will scan the image with specified rotation, horizontal and vertical scan. Each sample will be 32 by 32 pixels, and each sample will be sent to another generic filter. Finally, our generic filter 1 will render the recognized rectangles and send them to image display. Let's take a look at the code. Inside the event handler, we'll send start command to generic filter 2. We'll send the buffer for processing. And finally, we'll send a stop command. After that, we'll create a bitmap, convert the buffer to bitmap, create a graphics context in IGDI Plus to render the rectangles, iterate through all the detections, and for each detection, draw the rectangle and the text of the recognition. Release the graphics context, convert the bitmap to the output buffer, and release the temporary bitmap. Next, we'll look into the unprocessed data event handler for the generic filter 3. Here, we'll receive the samples from the sampler. Each buffer received from the sampler contains additional location information. We'll obtain it, get the detected position and angle, and assign them to member variables of the form. Next, we'll create features buffer, set the image format to grayscale, get pointers to the buffer and the image and assign normalized values from the image into the features buffer. Finally, we'll call predict on the classifier. The only remaining code is the onResult event handler of the classifier. Here, we'll check whether or not there is a recognition. If there is recognition, we'll get the category. We'll look through the already recorded recognitions to see if there is recognition at the current location and check if the new recognition is better than the previous one. If so, we will delete the previous recognition. If the previous recognition, however, was better, we will not add the new recognition. Finally, we'll add the new recognition to the list of detections. The project is ready. Let's try it. The recognition starts when the form is created. Since we are scanning a fairly large image with X and Y step and rotation, it will take a while for the recognition to be performed and the results to be shown. Here is the result of the recognition. You can see the locations of the recognized faces. The way the radio basic function classifier works, you can keep training it repeatedly, and this will change and hopefully improve the training. To demonstrate this, we will modify our training project. We'll add one additional loop, which will iterate 3 times, and we will leave the rest of the code the same and just save into a different file. Let's run the project. Open again the recognition project and load the new training. If we run the project, it will take longer to start as we use much bigger training. On some systems, it may take a couple of minutes to show the result. As you can see, now we have many more recognitions. You have to be careful with the training because it is easy to overtrain radio-based network and you'll get worse results. It takes time to find good set of training for good results. When we do recognition this way, first of all, it is fairly slow since we have to scan both with XY and rotation. Also, some rotated images may look like a face in different angle. This results in some false recognitions. This means that it is better to train with rotated images and have scanning only for X and Y position. The radio-based classifier in IntelligenceLab and some other of the classifiers there have a specific feature which is very useful for our need. We have the option to train not only with features, but also with weights associated with the features, effectively applying mask over features that we are not interested in. We'll use this method of training to train for the rotated images. We will apply mask on each image. Here is the mask. It's a white square inside a much bigger black square. The black area is going to be our masked area. We'll use this project for the training. In this project, we'll have 2 chains of filters. One will generate, rotate, and resize our mask. The other will generate, rotate, and resize the face. We will resize the faces and the mask to only 14 by 14 pixels to reduce the size of the training, improve the speed of the recognition, and also reduce some noise in the images. When we click the train button, we'll create a bitmap, we'll send a start command, we'll create an image buffer 32 by 32 pixels. We will iterate through all of the faces and their images, display this on a label. We will add one more category, which will be black color for background, and we'll assign category -1 as a background category. This will further constrain and improve our training. If I is different than 0, this means we are not training for the background and we have to load one of the bitmap files into the image buffer. We'll set the image buffer to grayscale. Then we'll iterate through all of the angles, set rotation for the two angles, force the image generator with the mask to generate a frame, and also send image buffer through generic filter 1. And we will allow the application to refresh. The mask image, after processing, will be sent to generic filter 3. In generic filter 3, we simply will set the buffer format to grayscale and will save the image for later usage into a member variable. Inside generic filter 2, we'll set the format of the input buffer to grayscale. We'll create features and mask buffers with the same size as the images. And we'll train the radio-based network classifier with the features, mask, and the category which we have assigned earlier. This is all the necessary code. Let's run and see how it works. If we click on the train button, you can see that the images are being rotated and the training is being created. This process will take a while because we are training with a lot of images rotated under a lot of angles, and we keep updating the user interface in the process. As the size of the training increases, the speed gets slower. The training is completed. Now we can close the application. Now that we have the rotated training, it's time to use it. We will load the training into the classifier. In our project, again, we'll use image generator with the same test image. We'll use component to change the video format to grayscale to speed up the processing. Inside the generic filter, the code will be almost identical to the one in the previous project, except the rectangles we draw will be bigger. In the scanning, we'll set the min and max rotation to 0, so we'll disable the rotation, and we'll set the size of the sample to 46 by 46 pixels to add the masking area. Then each sample received from the sampler will be resized to 14 by 14 pixels and sent to the generic filter. The image generator, again, is set for external clocking. When we create the form, we create a detection list and generate video frame. When the video frame is received, we extract the location information, make sure the image is in grayscale, and create features buffer and pass it for recognition. The radio basis function network can work with real or binary buffers as parameters. When using binary buffer, each sample is considered to be byte, and the classifier will perform internal normalization of each sample. The code in the classifier is much simpler since we don't care anymore whether or not there is previous recognition at the same location. These are all the necessary changes for the project to work. Let's run it and see the result. Here is the result of the recognition. You can see that it performs quite well, and with only one iteration of training. It also performs faster than the previous two projects. The next interesting aspect of using classifiers is that the feature extractor in front of the classifier has effect on the recognition. If you use more relevant features to feed the classifier, you will get a better prediction. We will demonstrate this with OCR application. Here again, we'll use radio-based classifier. We'll use training images, which are provided in the form of characters, spaces, pulses, and sharps. Sharps represent color of black, pulses color of gray, and spaces white. The training set is provided by the US Postal Service for testing character recognitions of numbers. They also provide corresponding file with labels for each image. The images are hand-scribbled. Our first task is to read those images from text and convert them into bitmaps. For this, we'll use a couple of helper functions. We will not go in details over the code, but in general, we'll read it in the form of string list, and then we'll parse the string list, and we will populate each pixel with the corresponding color, gray, black, or white. And we will do similar tasks for the labels. We will do that for the training images and the test images, populating two image lists and corresponding labels in the form of real buffers. When we click the train button, we will create a buffer extracting the features. For each image, we will convert the pixels to zeros and ones based on whether or not the pixel is white or non-white. Once, when we have created an array of buffers with those images, we will train the classifier with also the corresponding labels. After the classifier is trained, we'll create a set of test buffers. We'll iterate through those and we'll perform prediction. In the predict event, we'll simply assign the result to match the recognized category or -1 in case of error. After the prediction is performed, we'll display the result, and at the end, we'll display the number of errors and the percentage of correct prediction in label 1. Now we can run and test the application. If we click Train and Classify, we will see the result of the recognition. We have 109 errors of 1000 samples. which is 89.1% correct recognition. Here you can see what has been recognized properly and what has been recognized incorrectly. This is not a bad recognition rate. However, we can improve it somewhat by adding more relevant features. In this case, we used only the pixels as features for the recognition by calling this function. The result features buffer was just the size, width by height of the bitmap with values for its pixels inside. If we look at our images, we can see that there is one very obvious feature that we can use. This is the number of closed spaces inside images. A typical example is that 9, 0, and 6 have one such closed space, 8 has 2, and most other digits have 0. If we extract such feature and feed it to the classifier, we would expect to get a better result. VisionLab has a component that allows you to count the number of closed spaces in a shape. In this case, we'll connect generic filter to the connected components component, and inside its event, we'll set the number of connected components or zones minus 1 into the count zones. So if we have one surrounding zone of the digit, that would be considered 0. If we have two zones, like in case of 6, 9, or 0, one outside of the digit and one surrounded by the circle of the digit, then the count will be 1, and in case of 8, the count will be 2. Next, we will modify our extract image features function to add one more feature to the features, and in addition to the pixels, we'll send the image for processing through the generic filter, and as last feature of the result, we'll add somewhat normalized count of zones. Let's run this application and see the result. If we click Train and Classify, we will see a slightly better recognition. We have recognized correctly one more image, reducing the number of errors. Selecting a good training set is very important for the recognition, so spend enough time preparing and testing different training sets to get good results. As you have seen during the demonstration, performing artificial intelligence tasks is quite time and CPU consuming. There are multiple ways to improve the performance. You can try to optimize the training set, since smaller training in many classifiers will result in faster execution, but you can also speed up the execution by distributing it in parallel over multiple CPUs or cores. Alternatively, you can execute on general-purpose GPUs if the system has general-purpose GPU that allows execution of custom code. Distributed execution on multiple systems is another alternative. And finally, with the advent of FPGAs, execution of some classifiers on FPGA is becoming a viable alternative. Many of the components in the Mitov software libraries, including VisionLab and IntelligenceLab, have the capability to execute in parallel on multiple processors, or in case the system has OpenCL-enabled GPU inside the GPU. You can add this functionality by expanding the processing property, selecting engines, and adding parallel processing engine or GPU processing engine. In case of parallel processing engine, you can specify the priority of the threads for execution, the number of parallel threads, as well as other parameters for fine-tuning the execution. In case of OpenCL, you can select platform. Well, since this is a virtual machine, I don't have any OpenCL GPU platforms available, but on physical systems, you very often will have a list of platforms where you can select to execute the code. You can add those execution engines, and IntelligenceLab will attempt to use them if the necessary hardware is present. If the hardware is missing, they will not be used, and the execution will revert to a single CPU execution. I will leave you to experiment with those settings on your own and enjoy the improved performance. Finally, a few words for running artificial intelligence business. There is constant demand for better classifiers and implementations of existing classifiers. In traditional software development, the software is considered intellectual property, and that doesn't change with the artificial intelligence. But in case of artificial intelligence, the training itself also is considered intellectual property and a product of its own. This concludes our session. My name again is Boian Mitov, the president of Mitov Software. Mitov Software has a number of products for video processing, audio processing, digital signal processing, computer vision, data visualization, visual instrumentation, artificial intelligence, Boolean logic, universal animations, serial and TCP communication, visual live binding library, and a free advanced runtime library. We also developed the OpenWire Studio, a graphical development environment for Windows, and Visuino, a graphical development environment for Arduino. Mitov Software also supports the OpenWire open source library and the IGDI Plus open source library. Thank you for listening, and now it's time for questions and answers.
James has one here that's rather long. He says he's enjoyed this really excellent presentation, love seeing computer science implemented in Delphi, and he read your recent articles in Blaise Pascal magazine. He says, you notice you use a black background when attempting to detect rotated facial images. In real life, say for airport security application, the background would typically be quite a bit brighter as well as noisier in each frame, grabbed for scanning against the target of library faces. With real world in mind, have you tried your AI facial recognition example with a variety of background colors and brightness settings? If so, can you share some further results you've had? If not, what should we expect to be the next challenges to overcome with the classifier?
Actually, yes, I have used the classifiers and similar techniques in real life scenarios. I showed already the masking capability, and what is quite interesting, it is quite unique to IntelligenceLab. It's a technology which I have largely developed, and I have not seen in other classifiers which are popularly available. In essence, if you use the weighting around the sample, you can specify arbitrary shapes around the face, and in this case the classifier focuses only on those and actually excludes pretty much anything that's around the face. Then the classifier becomes quite precise in terms of ignoring things that are around the face, including any kind of noisy background and stuff. That's number one. Number two, I have not done it specifically with faces, but I have done it with detecting humans in a noisy environment, in particular swimming pools, which are, notoriously noisy. with water, reflections, and everything else. And the classification worked. In that case, we used KNN classifier. We got better results from it than with the radio-based functional classifiers, but they both perform quite well, even in such noisy environment as a swimming pool, recognizing whether or not there is human or anything else in the pool. So yes, it works in noisy environments, and yes, there are ways to do it. It just requires good training, and I mean, it's training is a time-consuming task, and it's sometimes nerve-wracking task, but it's a very critical task when you're dealing with artificial intelligence.
I love the idea that I have to train my software to do things. Well, it's an interesting idea, at least to say the least. I've written the software, now I have to train it to actually do what I want it to do. Fantastic.
Yeah, it is a different world and different perspective, and that's why I had the last slide, which was on the business of artificial intelligence. Training is a lot of work, and it's a product, and it's intellectual property, and as such, I mean, yes, this is the right slide. As such, it's a product of its own. So yes, you have to write the software, but you also have to spend the time and effort and money to actually train it. So both are products, and both have their own value.
I remember Google had an open source collection of trainings they did for recognizing dogs. It was like, I'm sure they have lots of useful things, but you can download this that will recognize dogs. So for use in things. Is this cross-platform? Does it work on other platforms like Android and iOS and macOS?
Actually, IntelligenceLab is one of the few products that are already ported to cross-platform. I believe, if I remember correctly, I did some experimenting with Mac. I don't think I have. It compiles for Android, but I have not had chance to play with it under Android, other than just compiling and running it quickly to see that it actually fundamentally works. I just don't have iOS device, so I have never spent the time to add support for iOS. But if somebody comes with big buck and says, "Well, hey, we really need the iOS support, and we can buy quite a few licenses," that will be no-brainer to add, since the code is completely platform independent. I have written the IntelligenceLab code completely in Delphi, so there is nothing platform specific into it.
It sounds like it's fairly CPU, GPU intensive. Is that going to be a major issue on a mobile device, or do you think that the mobile devices are going to have the horsepower to deal with something like that?
It is computationally intensive in general. It totally depends of what you're detecting and how big your training is, things like that, and which particular classifier you're running. So some classifiers are more computationally intensive than others. And again, I'm also working on adding the capability, I hope to see it in a year or two, adding the capability of not only executing on one device and utilizing parallel execution or GPU in the device, but I want to expand that so you can utilize cluster of devices and execute your classification over cluster of computers connected over the network. So then you can have the classification component running inside a mobile device, and then if the mobile device can connect to the clusters, we'll execute on them. Otherwise, we'll try to execute it slower on the device. In general, yeah, I mean, it's going to be slower. I have not experimented to see how much slower, but yeah, so some of the tasks are complex. Some are easy, some are complex. That's why most mobile devices, they tend to send the images and other stuff for processing over the web, but sometimes you want to do it locally even when you're completely disconnected. So it totally depends.
Okay, that's a cool idea. I like that idea of doing that, doing the cluster thing. What's the best component to use for facial recognition?
For facial recognition, one of the best components is actually in VisionLab. We didn't cover it here because I wanted to focus on IntelligenceLab. Actually, I stand corrected. That component is good for facial detection. When we talk about faces, there are two aspects of it. There is a facial detection, which detects universally faces, and then there is facial recognition, which recognizes specific face between multitude of faces. For facial detection, HAR or HOC are probably quite good components. For facial recognition, actually the RBF component which I showed is quite good because it tends to self-optimize, it tends to optimize over time, and it uses relatively speaking, smaller training knowledge base compared to, as example, something like KNN classifier. KNN classifier performs very well, but the KNN classifier, the knowledge grows very rapidly and can really overwhelm the system. So, yeah, I tend to pick between KNN and RBF at present. There may be, I mean, other people may have different opinion and they may have different ideas. I have not experimented with deep learning yet. I am planning to do so in the coming months, as time permits. That would be another interesting one to research. Again, based on my current experience, RBF is a good starting point for facial recognition to distinguish between different faces. That's what I can say.
Okay, very cool. Have you tried applying your library to stock market prediction, like recognizing the most typical price patterns and such, etc.?
No, I typically have used them just because of the nature of the work I do. I typically have used them for image recognition and tasks like that. I am planning to play a little bit with speech recognition and voice recognition. I was trying to add that to this session, but just the time did not allow me to do the necessary research work and prepare a good training set for speech recognition. Hopefully next year. I have not done it for price tracking. It's just not something I have specifically worked on. But there should not be a big issue with that. Over the weekend, I was at Code Camp here in Los Angeles, and somebody asked similar question for the stock market, and we had a discussion, and I gave some pointers at how predictions can be done if the idea is for predictions. What you can do is you can take a set of data, historical data, let's say for the last week of prices, and use that as features. You can also use things like the time of the day and the day of the week as features, and feeding such sets of data, then you can train with whatever you want to predict, whether or not it's a buy or sell opportunity, or whether or not it's a prediction for a target price. You can train the classifier for that and see how well it's going to perform. Maybe for this type of prediction, I would try neural networks. Although they're kind of old-fashioned, they may do good job for this particular task because the task is linear in nature. So the thing is, in my experience, in terms of classifiers, they tend to be two types. They tend to be more discrete type of classifiers, which are similar to the ones we use here, like radio-based function, and they are much more analog type of classifiers, which are kind of like non-interrupted function, and that would be something like neural network. So since the prices, they're in essence a function more or less, neural network maybe will give better results. But again, I mean, you can get probably good results with discrete classifier too, so it's worth trying that one as well. But I will try the neural network first to see what's going to happen.
Excellent, great idea. Great suggestions. James also says thanks for great detailed responses, and Mark's asking where he can get your samples.
Yeah, I will upload the samples. I was recording videos until this morning, as Jim will tell you.
Yeah.
So, and I'm recording one more video for the tomorrow session. As soon as this is cleared, probably sometime this evening or tomorrow, I will put the samples on my blog, and my blog is available through my website. So I can never remember the blog itself, but if you go to the mitov.com, in the menu you can find link to the blog. Can you put it on the screen, Jim?
Yeah.
So yeah, if you go to support blog, yeah, this is where I'm gonna post the samples. Yeah, I'm sorry I did not have chance to put them there yet.
Okay, great. Well, I'll put a link here in the chat window.
Thank you.
Stay tuned to, and everybody can grab those when they show up in the near future and download the trials. So this was like, what was this, something you were doing here at?
Yeah, this was the Mini Maker Fair here in one of the Barnes and Nobles, and I was doing some Visuino and robots programming and some other stuff, as you can see. And generally speaking, was having quite some good time.
I bet. It looks like it. I know. I always see all your posts on social media, and you're like, "Oh, look at these great new gas sensors I got," or something like that. And I'm like, "Oh my goodness, Boian's out there having all the fun, making all the cool tech," which I guess we're going to see. Oh, was that?
Yeah, this is called CAM, by the way. I was presenting Delphi, and that, I mean, yeah, I was pretty much very few people, unfortunately, knew Delphi, but I hope I have created a few fans there. So, yeah, I had a Delphi session there, and there were quite some people.
Fantastic.
It was fun.
Okay, great. Well, thanks again for that session, and thanks for all the time you put into these.